Okay, so the recitation materials for chapter 23 are long, so important to remember that chapter 23 is taking a week and a half of class time for us, and so I'm going to break this up into a couple of videos. So what I want to do in this video is go over the answers to the questions that are not ray diagrams, and then in a future video, or maybe even two, depending on how long it takes to get through those, I will go over the answers to all the ray diagrams. So I have up here on the screen the first question, which says I have an object placed in front of a mirror. The observer is positioned as shown, so the observer is over here. Which of the points shown best indicates where the observer would perceive the image to be located? And so we have here, right, the observer is here and the object is here. And for a flat plane mirror, the image is always, the answer to this is going to be C, okay? So when we look into a mirror, we see an image, and that is a virtual image because rays don't really come from that spot, that appears to be coming from a spot behind the mirror, exactly the same distance away from the mirror behind the mirror as the real object is in front of the mirror. So the answer to this one is C. The focal length of a concave mirror is what? The distance at which an image is formed, that's not true, okay? So A is incorrect, right? Rays that enter we have a concave mirror. So let's get a drawing of what a concave mirror looks like. A concave mirror looks like this. And rays that enter my concave mirror will, if they enter parallel, will all bend such that they exit through the focal point of this mirror. And that makes it seem like A should be the right answer, but A is the wrong answer because this is only true for rays that enter parallel. So A is not correct. The distance at which an object must be placed to form an image. I think I cut off the words to form with this figure. Sorry about that. That's incorrect. C says the distance at which parallel light rays are focused, and that is the correct answer to this question for the reasons that we just talked about right here. And D is the distance from surface of the mirror to the back surface of the mirror. No, that's not correct either. The second, number 2, says what is the index of refraction of the plastic if a ray is refracted as in the figure. So let's get that up and work through it. So for 3, the answer to this was C. For 3, the formula for index for Snell's law is N1 sine theta 1 equals N2 sine theta 2. Okay, so this is the first medium. So the 1s go with the first medium, the 2s go with the second medium. And so what we can see here is that, right, the air will be the 1s. So this is air. Because it's entering from the air and traveling into the plastic. And this will be the plastic. N is the index of refraction. It's a unitless number, and N equals 1 for air, and it goes up from there, or air or a vacuum. Okay, and theta is the angle of incidence. And we always measure the angle of incidence relative to the normal. So this method of measuring the angle is the same, sorry, I cut that off a little bit. This method of measuring the angle is the same method that we used in chapter 20 to measure the angle for that was magnetic flux angles. So we're imagining a perpendicular line, and the angle relative to that perpendicular line. So let me draw out what I mean by that. So here's the plastic, and here's the water, or the air. And we have this line right here is the normal line. Okay, so we want to measure, this is the interface between the two things, and we want to measure what is the angle relative to this dashed line that I've drawn here. So this says that this angle here is 45 degrees, and it comes in that way, and that this angle here is 55 degrees, and it goes out that way. And these are purposely not labeled as the thetas that should go in this equation, okay? So this right here is a right angle. That's what normal means. It means that it makes a right angle with the surface. So 45 plus whatever this angle is should equal 90. 45 plus 45 equals 90, so I'll put in 45 there. 55 plus some number equals 90, so that number there is 35 degrees. Okay, so that's theta 2, and this is theta 1, like that. The index of refraction for these two things are here, and we are looking for the index of refraction N2. So we know theta 1, we know theta 2, we know N1 is just 1, and we're solving for N2. So I will use this formula here. I want to solve for N2, so I'll divide by sine theta 2 on both sides. And my sine theta 2's cancel, and N2 equals these three numbers together. So I have room here. N2 is N1, which is 1, times sine of theta 1, which we found to be 45, divided by sine of theta 2, which we found to be 35, like that. You plug all those numbers in, and I actually got my calculator out for this, so we'll do 1. Oh, it stopped working. Awesome. This calculator is only so helpful. It kind of stops working after a few minutes. So I'm going to go ahead and close that and open it back up again. It did not come back up, so we'll just skip it. So sine 45 divided by sine 35 is 1. Okay. The next problem says that I have a laser beam is passing from medium 1 to medium 2 as shown, and we want to say what is true about these two things. Okay, so here's medium 2 and here's medium 1, and I have something that's coming in at a fairly shallow angle, and it bends and comes out at a little bit steeper angle like that. Okay, so you can reason through this if you want. And the way to reason through this, and I thought I pulled it up, but I didn't, so I'm going to get it up now, is to probably put something on your note card or commit something to memory which says, just a second, it will come. Right here. So let me make this bigger. It says that light moving into a slower medium will bend toward the normal, and light moving into a faster medium will bend away from the normal. Okay, and so Okay, so the ray has done, so I'll draw in my normal line. So I'll draw in my normal line. So I drew in this dashed thing. So this angle here must be theta 1, and this angle here must be theta 2. Okay, so bending toward or away from the normal. This is an example of something bends away from the normal. Okay, right, theta 1 is smaller than theta 2. Okay, so it has bent away from the normal. If it had bent toward the normal, that would be something that kind of exited like this, where now theta 2 would be closer, this angle here, this outgoing ray would be closer to the normal line that I've drawn instead of farther away. Okay, so it bends away from the normal, and we can just check this out here and say light moving into a faster medium bends away from the normal. So it's moving into a faster medium. N is smallest for a vacuum. And that is the fastest medium. Okay, so by fast and slow, what I mean is the speed of light fast or slow? The speed of light is fastest in a vacuum, and that is where N is the smallest. Okay, so if it's moving into a faster medium, that must mean that it is moving toward a smaller N. So N2 is smaller. I will just say right now that I find this way of thinking about this problem to be really hard and confusing, and I get it wrong half of the time because I have a hard time, like, kind of, I have to like memorize these statements, and from year to year I always forget these statements. An easier way for me is that lawnmower example that I gave in the lecture slides, which is that I imagine pushing a lawnmower from this medium to this medium, okay? And at this spot here, I'm gonna hit a spot where, if you think about these being the two front wheels of my lawnmower, where this wheel is in one medium, and this wheel right here is in another medium. And this wheel that's in this medium, if it's the faster medium, which it is, we just kind of figured that out, is going to move more than this one is right here. You can kind of imagine driving your lawnmower from grass onto sidewalk here, the slower medium into a faster medium. And as you hit this interface, right, this wheel right here will curve more than that wheel does. So that is another way of saying that this is the faster medium, and this is the slower medium. Speed of light, and there's the slower speed of light. So that works too. So you can kind of reason it however you want, but it must be that N1 is bigger. So if we go back to where we were, which was here, I believe, we will say that the answer to this is B. N1 is greater than N2. Okay, let's do the next one. A fish in an aquarium with flat sides looks out at a hungry cat, and what does the cat look like to the fish? So I said flat sides, but my little picture here is a fish with curved side, in an aquarium with curved sides. So I'll draw it that way on my piece of paper. So here's number 4. And let's draw my fish in a tank of water. and my cat out here. I'll draw his nose. Okay, so from the perspective of the fish, how does the cat look? Okay, so what I want to do is I want to imagine some rays that are leaving the cat, and I'll just draw them leaving the cat's nose. They're going to travel from air, from that fast medium into the slow medium. So they're going to travel from air into water. And as they do that, they're going to bend. And then we're going to see how they are perceived to a fish or any other thing inside the water. So let's go ahead and draw this. So I don't want to think about this ray right here coming from the cat's nose is just going to travel on a straight line, right? So if it doesn't hit at an angle, then it won't bend. So let's go imagine a ray traveling at an angle like that. I guess I'll make my fish a little bigger so we can see what would happen with this ray. So I'm going to use my lawnmower example. But you're welcome to use the other example that we just went through for figuring this out. So if I imagine my lawnmower, I'm going to hit right here, and eventually it's going to be here where I have a wheel in the slow medium and a wheel in the fast medium. So I know that this is the slow medium because this is water, and this out here is air. And right, we know that the speed of light is the fastest in a vacuum, and it slows down as it goes into denser and denser media. Okay, so this is the fast. This is my sidewalk, if you will, and this is the slow. So we get a wheel here and a wheel here, and if air is fast, that means that this wheel is going to turn more than that wheel will. Now let's draw my normal, and we'll see that this line here is going to bend toward the normal. So just to kind of pull this up here, right, light moving into a slower medium, so that's the one on the top, will bend toward the normal, and that's just what we've drawn. So it fits with what's written there as well, if you don't like the way of thinking about the lawnmower. Okay, so now if we are a fish, we don't think that this ray is coming from here. What we want to do is trace back this outgoing ray like that. Okay, so according to the fish, right, the ray is really going through here, bending, and going like that. But if you put a fish right here, maybe I should put my fish right here. According to this fish, this ray seems like it's coming along this line here. So let's go ahead, there's this unbent line, so let's just go ahead and trace this unbent line as well. And there you go. That is where the fish thinks that the cat's nose is. So, right, we've kind of traced back our two real rays are coming here and there. And if we trace both of those rays back to a spot where they appear to be coming from, that would be a virtual image of the fish. Right, the rays appear to be coming from here, which is a spot that is farther away. So C is the answer to this question. Let's do number 5. Right here. So I have light rays are converging to point 1. The lens is inserted into the rays with its focal point at point 1, and which picture shows the rays leaving the lens? So make this a little bit bigger. Okay, so what I know, let me put this on a piece of paper, is this is right here is a diverging lens. So it's going to take incoming light rays and spread them out. So what I have here is a group of light rays that are converging to a point. And I'm going to insert this diverging lens and move it up so it gets in the way. So what I know is that those rays are going to exit this lens more spread out than they were before. And it says that the lens is inserted into the rays with its focal point at point 1. Okay, so basically these are rays that are coming in and they are on their way to point 1. So let's draw what this looks like from a ray diagram perspective. Is that I have now some rays that are entering on their way to point 1, which the problem said is the focal point of this lens. So I have a bunch of incoming light rays. I'll kind of draw the center line of this lens. They are entering here. And this ray starts out and it's on its way to F. This next ray starts out like this, on its way to F. This ray right here starts out like this, on its way to F. Like that. Okay, so there's all my entering rays. Ray for a diverging lens like this, we know that rays, right, we have these 3 rays. There are 3 rules for drawing ray diagrams: is in through F, out parallel. Ray 2 is in parallel, out through F. And ray 3 is in through center, principal axis, doesn't bend. So these rays are trying to do this. Okay, so the rule of drawing ray diagrams for a diverging lens is that these are actually the rays that are coming in through F. They never actually make it to F, but that's how that rule goes. So they're coming in through F, they're going to bend and exit this, coming out parallel like that. So the answer to this is D. Number 6 is that I have rays enter a glass prism, and which is a possible path for the ray through the prism. And let's get a new piece of paper out for this. So let's figure out what goes on with rays that come in parallel to a prism. So a ray comes in like this, and we'll figure out which is the fast medium and the slow medium. So this is glass, and out here is air. So this must be slow. So my sidewalk is out here, and my grass is in here. As this ray enters, it's going to end up like that. So one wheel is in the fast medium, that's this one out here. So that's side is gonna bend more. This wheel here is in the slow medium, it's gonna bend less. So this is gonna bend down like that. Following those rules, here where we say light moving into a slower medium will bend toward the normal. Now drawing my normal is a little bit different. So drawing the normal, so this is the surface, so I need to draw something perpendicular to that surface. Okay, and so this is theta 1. And so it's moving into a slower medium, so it should bend toward the normal. And sure enough, theta 2 is that one. So theta 1 is bigger than theta 2, and that is another ray bending toward the normal. But it's generally a little bit harder to see people have a hard time seeing that because it's at this tilted angle. Okay, so that's what it does in the first one. So we can immediately cross off A and C as not being correct, but we don't yet know B or D. So now I'll use my lawnmower example. Now I'm going from slow into fast. So this is the fast medium. So this is the side that will move more. And this is going to bend down again. If we use this rule about the normal, there's my normal line. So I draw this line here and that line there are perpendicular to each other. And now angle 1 would be this one, right? The line relative to the normal. And angle 2 is this one. So theta 1 here is smaller than theta 2 is, and this is something that has bent away from the normal. And if I come back to my rule, light moving into a faster medium, which is what we were doing, right? We're moving from glass, the slow medium, now into air, the faster medium, bends away from the normal, just like we just discovered. Okay. So these next several problems I'm going to do in a future video are looking at different ray diagrams for various different setups. As part of your homework for this, I do have you turning in your homework. I want you to turn in some paper copies or photographs, I guess, photograph copies of digital solutions to the homework problems. So if you're struggling with any sort of ray diagram, they're all more or less covered in these recitation problems, as well as in some of the lecture PowerPoints as well. So that's a resource to check out in the next video. But let's do the last couple here. So which lens is converging, which lens is diverging, and how do you know? So we'll look over here on the left-hand side. You actually, if you're in my lab, you have converging and diverging lenses in your lab kits, and I highly encourage you to pull them out and get used to looking at them and what they look like, because that is a frequent question on a test that I put up there is like I show you a picture and ask you what kind of a lens it is. So this one over here on the left is converging. This one over here on the right is diverging. And doing ray diagrams will help with all of this. But another thing that is helpful with all of this is this table that I have at the end of the PowerPoint slides. Oh. Right here, which says that for a converging lens, we will see that it's smaller. Oh, so I guess first we should come back to this and say that what we are viewing as we look through this lenses is the image. So I can see here that this guy here on the left, his eye, that's the image of his eye, looks bigger than the actual object of his eye. Okay, so for number, what number is this, 12? Eye image is bigger than true eye. And of course that true eye is the object. Okay, so I have, I'm looking for something to be bigger, and let's go through and see what we can see to find something that is bigger. So this is smaller, this is smaller, this is smaller, this is smaller, right? A diverging lens always makes a smaller image. So there's no way that this thing on the left-hand side is a diverging lens, or a concave lens. It must be a converging lens. And we can actually figure out exactly where it is. This down here on the bottom is the only one that makes sense. It's larger, so we can rule out the smaller, right? Because we have just rationalized that the image of the eye is larger than the object. So we're down here in the larger, and we can actually tell if it's which one of these two it is by the fact that we saw an upright image of the eye. It's not inverted. So this is a virtual, upright, and larger image of the eye. The only place that that is possible is if the object is inside the focal length of an eye. So what this is saying is that this is a converging lens. This guy's eye is not upside down. So because his eye is not upside down, his eye is inside the focal length of the lens, which must mean that his eye is really close to the lens, which is what we see here. So this is a converging lens, and I'll go ahead and add that the object is inside F. So we can say DO is less than F. Okay, for this next one over here, what type of mirror is shown and how do you, oh, I guess we're not done with this one over here. So on the right-hand side, we are looking for an upright right? Not inverted, an upright and smaller image. And if we come over here to the PowerPoint, um, virtual, upright, and smaller is true for all of these. So it doesn't matter where the object is, you will always have a virtual, upright, and smaller image formed when you are using a diverging lens like that. Okay, let's go over to the next one here. So this says, what type of mirror is shown here and how do you know? And so what I'm noticing here is that this guy is looking at an image of himself, and I see that there's an upright image of himself here. But actually, if I look in the backgrounds, it's upside down. See, this right here is an exit light. So this is an exit light that would normally be on the ceiling. So this is the ceiling up here and the floor down here. So somehow we have an upright image that is larger, right? The image is larger than the actual person. We have an upright and larger image in one portion of the mirror and an inverted image in the background. So let's go look for that. And I think we are most certainly looking in this thing. So, right, the man that is very close, where he's very close, he is upright and larger because he is inside the focal length of this mirror. So his upright image is here, and everything else that is outside the focal length, so he's farther away than the focal length of the lens, is here, where these are real images, but they are inverted. So this must be a concave mirror, because that is what a concave mirror does. If this was a convex mirror, then we would be looking at upright and smaller images throughout, which is not what we see. Okay, so just to kind of throw this over, the left-hand side was a converging lens, the right-hand side of 12 was a diverging lens. Another word for diverging is concave. Another word for converging is convex. And in 13, this must be a concave mirror because we see a virtual, well, we don't know that it's virtual, so I'll stop with virtual, but we see an upright and larger image of man. Very close to the mirror. And since he's very close to the mirror, the reasonable assumption here is that that must be that the object is inside the focal length. And we see inverted images of the room in the distance. And you all have spoons at home, metal spoons. You can do exactly this experiment with a metal spoon. And so experiment around with trying to find the virtual upright and larger images for an object very close to a metal spoon, and then as you get farther away, you can find those inverted upside down images in a metal spoon. Let's see, there is one more here. You see an upright magnified image of your face when you look into a cosmetic mirror. This means that the image must be, is it in front of the mirror surface, on the mirror surface, behind the mirror surface, or only in your mind because it's a virtual image. This would be true for any mirror, but and I guess I will return you all the way back to question 1, right over here, where we say that the object is always behind the mirror, okay? Or sorry, the object is in front of the mirror. The image of the object is always going to be behind the mirror. So if we come back here, we don't need to even figure out what kind of mirror this is, right? The image is behind the mirror surface. If you see an upright magnified image of your face when looking into this mirror, we can go here and say upright and magnified. Upright, smaller, upright, smaller, upright, smaller, upright, and larger, we must be here. So we must be here. So this must be a concave mirror. It's virtual, upright, and larger. Um, and so we can kind of reason this a little bit more and say that 14, this is a virtual, upright, and larger image is only from a convex mirror with the object, this would be your face, the object inside the focal length, so the distance to the object, right? If your face is here, I'll draw an eyeball for your face. It must be the focal length of the mirror, looks like this, and this is the distance to the object. So the distance to the object is less than the focal length, and that's how we can say that this is something that comes from a convex mirror with DO less than F. But this is sort of superfluous to the answer to this question, right? The answer for any mirror is that the image is behind the mirror surface. Or actually, let me back up on that. It's not always behind the mirror surface. It's behind the mirror surface because we know that it's a virtual image. So I guess I should, back that up just a little bit. And because this is upright and larger, we know that it has to be this virtual image. A single lens or mirror a real image that comes from a single mirror or lens will always be inverted. It will always be upside down. The fact that this is upright tells me that this has to be a virtual image. And a virtual image is not where rays really cross. So a real image would be formed over here on the left-hand side of the mirror. A virtual image will be formed over here, back behind the mirror. The rays can't actually be coming from back behind the mirror. So they're going to travel. So this must be the location of a virtual image.